In this video, we're going to be talking about continuity and how limits play a part in that, which is essentially going to tie into section 2.4 in your book. And what we're going to try to do, first of all, is understand what does a continuous function mean, what are the different types of discontinuities that can exist, and what are they called, and what do they look like. And then we're going to look at how would you be able to determine if a function was continuous at a particular point, which is really sort of our goal here. And eventually, down the road, we're going to see a relationship between continuity and the ability to take a derivative at that same point. But for now, let's just kind of decide what continuity is going to look like. First of all, we need a definition of what continuity is, and we're going to make that definition in terms of limits. In order for a function to be continuous at a point, it has to fulfill three basic requirements. So a function is going to be continuous at some point, and we're going to call that point x equals c to stay consistent with our notation. Function f is going to be continuous at c if and only if the following three conditions are met. First of all, f of c must exist. So it has to be defined at that point. If you have a hole in the graph at that point and the function is not defined to be equal to some other value, then the function can't be continuous there. Second of all, the limit as x approaches c of f of x must also exist, so there has to be a limit there. And last but not least, that limit that we said exists in the previous step has to be equal to the function value at c. Now this is all a very formal way of saying something very simple. In order for function f to be continuous at some point x equals c, I need to be able to draw the graph at that point without having to lift my pencil from the paper. That is a good sort of intuitive sense of what continuity is. So let's make a picture or two and let's see if we can come up with some examples of continuity. So I'm going to get rid of this definition. Let's say that I have a graph and my value c is here. And let's say that I draw my graph, and as I draw through c, I never lift my pen from the paper. We would definitely say that at c right here, there is, first of all, going to be a value called f of c. So I can visually see there's a function value at that point. I can see there's going to be a limit as x approaches c, because I can't evaluate the function at that point. And I can clearly see that they're going to be the same. So this function f is continuous at c. No problem. If, on the other hand, at c, I actually have a hole like this, so that when I draw my function, I would have to pick up my pencil at c and leave a gap. And notice that the function, not only is it not defined there at c, f of c does not exist, but I can visually see that I'm going to have to pick up my pencil. That would indicate that the function f is not continuous at c. At x equals c. Now you might say, well, what happens if there's a defined value, it's just someplace else? So for example, let's say that f of c is defined in that particular case. Does that make the function continuous? Well, not really, because again, when I get to c, I'd still have to pick up my pen, put it down, put the extra dot, and then put it back again to draw the function. So still not continuous, even if f of c is defined, if it's defined to be something else. Okay. Now, if you'll take a look, in your book there's a good summary, and it's on page 46. Okay, so page 46 looks something like this. There's a great picture here that gives us a picture of different types of discontinuities that can happen. And so we want to get an idea of what that's going to be like. So notice that in this upper left-hand corner, we have this idea of a removable discontinuity, both where f of c is not defined in the upper left-hand corner, which is here. Oops. And when f of c is defined to be something else, which is here. So in both of those cases, we do not have a continuous function. We also have a new kind of function we haven't talked about yet, which is called a step discontinuity. It's exactly what it sounds like. It's like the function takes a step at a particular point from one value to another. This is usually when we have what's called a piecewise function, and we'll see an example of that in just a minute, where the function is broken up into two pieces on either side of C. Obviously, in order to draw this, I have to pick up my pencil from one section to the other. The other type of discontinuity we can have is an infinite one, which is shown here using an asymptote. And so in those particular cases, obviously the function, again, cannot be continuous because there's no way I could draw that without picking up my pencil. We do have a continuous function that sometimes has a feature called a cusp right here. And notice that the cusp is really just a pointy spot. They call it in your book a sharp point or an abrupt change of direction. But basically, in order to draw that, I certainly could draw my pen up to the cusp and keep going without lifting it. So it can be continuous at those points. Those are going to be special points that we're going to focus on later when we're looking at derivatives. And last but not least, we have just a plain old continuous function. So this set of diagrams is actually pretty useful. So we also want to talk a little bit about limits, because notice that one of the conditions for continuity is the fact that you have to have the limit as x approaches c of f of x must exist. This section introduces us to this notion of something called a one-sided limit. And basically what that means is when we are approaching c, we can approach it from either the left or the right. If I approach c from the left, I'm approaching it from values that are less than c. If I approach it from the right, I'm using values that are slightly larger than c. And so we can break this up into two limits. One of them is the limit as x approaches c, and then we're going to put a little minus right here, which is essentially saying if I'm coming at c from the left or from below, either way. In the other case, we're going to take a look at the limit as x approaches c from the right. And in that case, basically, in order for the limit to exist, these two limits need to be approaching the same number. If they're approaching two very different numbers, we could have a step continuity, a step discontinuity at work. All right, pause the video for a moment. Find exploration 2-4a, which is called continuous and discontinuous functions. And once you've found that, it asks you to plot the graph for k equals 1 and sketch the result on your paper. It also asks you to say what it means for a function to be discontinuous in number 2. So go ahead and try to answer those two things. Put the function in your grapher. Also, tell what it means for the function to be discontinuous at x equals 2. Okay, so here's the function, and the two pieces of it are f of x equals x plus 1 whenever x is less than 2. That's this little section off the linear looking section. And then the other part says f of x equals k times the quantity x minus 5 squared, and that's when x is greater than or equal to 2. And we have plotted this for k equals 1. So our two pieces are x plus 1 when x is less than 2, and x minus 5 quantity squared when x is greater than or equal to 2. Clearly this function is not continuous at x equals 2. It has a discontinuity called a step discontinuity. So what does it mean for it to be discontinuous? Well, in this case, we could certainly make the argument that at x equals 2, right at this point right in here, if I try to approach x equals 2 from the left, it looks like my function value that I'm going to approach is roughly y equals 3. On the other side, it clearly is approaching a larger positive value, something like y equals 9. And so the two functions are just approaching two values. So the limit, when we try to approach c equals 2, just simply doesn't exist. We're approaching two different values visibly that would happen in a table or whatnot. So if we look at the left-hand limit, which is the next part of our exploration here, I'm going to go ahead and get rid of my picture. As I approach the value x equals 2 from the left, I am going to visibly be able to find out that that's going to be 3. I can tell that from my graph. I could tell that from a table. There's lots of ways that I could tell what that is. The function is not defined to be 3 at that point, but that's certainly the limit of what it's approaching. On the other hand, if I approach from the right, I'm clearly going to be approaching the value of 9. These two limits must be the same in order for f to be continuous at this point, and obviously they're not. So we would just say these two limits must be equal for the function to be continuous at 2. Now, while I'm writing this, I also want to say one other thing. The function could be continuous everywhere else. In other words, just because I say that it's not continuous at x equals 2 doesn't mean it can't be continuous at lots of other places. We're really just focused in on this one point. So understand right now we're talking continuity at a particular point. Now the next part of our exploration says, okay, fine. The function's clearly not continuous at x equals 2. Could you find some place where it is? Notice that you had that parabola and that linear piece, and the parabola, we can mess with how far open that parabola is. Could we make it come out differently? Let me show you what we're aiming for. So take a look at this function. In this particular function, you can see that I have the parabola open more widely than it was before, and right here at this point we've formed a cusp where the two functions actually do meet and we have a continuous function. The only question is, what value did I plug into my calculator to make that graph work? All I did was change k, but what value of k would work? This is a pretty simple amount of algebra that we're going to do here. We're going to say, in order for those two things to work, that x plus 1, which is part of the piecewise function, needs to somehow be equal to k times x minus 5 quantity squared. And if we could just figure out the value of k that makes those two things equal, we'd be in good shape. So we need to solve this equation and find out what values of k make it work. So let's try that. Pause the video for just a minute and see if you can solve for k, in this case, to make this function turn out to be equal. Okay, so to solve this for k, we have to remember that we are very interested in what happens when x equals 2. So if we plug in x equals 2 on the left side, we get 2 plus 1, or 3. If we plug in x equals 2 on the right side, we get quantity 2 minus 5 squared, or we're going to end up with 9 times k. When we solve that for k, we get k equals 1/3. If you stop the video, plug in 1/3 where we had a 1 before, and get your graph working, you should find the graph becomes continuous now, and you'll see the cusp at x equals 2. So you can take a moment to pause the video to do that. Number 6 on your exploration asks you to do one more thing. It says, suppose someone asks, is f of x increasing or decreasing at x equals 2 with k as in problem 4? So in other words, for our new graph, we know it's continuous, but is it increasing or is it decreasing? And so let's take a look at that. If you go back to the picture, let me get rid of my... Okay, so at this point right here, we want to know, is the function increasing or decreasing? And it's really hard to say, because it abruptly changes direction right at x equals 2. It was increasing, but then immediately when we move to the right of x equals 2, it begins decreasing. We can't really conclusively answer the question. We have to say that it makes this abrupt change of direction. What we're going to find out is that at this cusp, we're not going to be able to define a derivative. Why? Because if we try to take points on either side of it to create that little slope formula, we're going to have a very difficult time, because depending on where we pick them, we're going to have radically different slope values, some positive, some negative, and they're going to be all over the place. So at a cusp, we're actually not going to have a derivative. We're going to see that more as we get into chapter 3, but for now it's just something we want to notice.